Okay, yeah, thank you so much. I'm Matthias. This is joint work with Sarah Karen from Technion. I think she was going to join via Zoom, but I think something came up, but I'll be here. This talk is on collaboration promoting resilience, meaning ability to deal with unexpected changes. So we have in mind situations where robots or agents can collaborate, but don't necessarily have to. So for instance, if you look at the picture on the left here, there's two robots, they have to move a tool each from point A to B. They could each just grab their own item and move it to their own target and be done with it. But if there's an unexpected change in the environment, for instance, an obstacle blocking the way, then if they're just acting individually, there's nothing they can do, they can't complete the task. On the other hand, if they had learned beforehand already that they can collaborate and pass the item from one to the other, then maybe they could still complete the task even with the obstacle. So this is what this talk is about. There's a lot of prior work on collaboration and communication, sort of non-zero shot, non-ad hoc, that all deals with maximizing utility. And we are thinking about, does it also help deal with unexpected things? So in terms of the language of ad hoc teamwork, you can kind of think of this as zero shot, but with a twist, rather than caring about what happens if the other agents I'm dealing with, if they change, can I zero shot or few shot adapt to that? And thinking of the other agents as a problem, we want to think about whether the other agents could be an asset and something we can leverage, so that if something in the world changes unexpectedly, we can zero shot or few shot adjust to changes in the environment. There's a few different parts to this. For instance, what does it even mean to facilitate collaboration? In this talk, we want to mostly talk about how we define resilience. It's all part of sort of a bigger research agenda we have, and that we think that this sort of fundamental problem definition could be interesting to others as well. So intuitively, what we want to formalize is the idea that if there's a small or somehow bounded in magnitude change in the environment, that should also lead at most or at worst to a small drop in performance. There's a ton of different ways you could formalize that. We've picked a few different ones in our own work. We kind of require two key ingredients to make that work formally. One is we need a distance measure between two MDPs, or POMDPs or Markov games, whichever formalism you're working in, so that if the environment changes, we can somehow measure or quantify how much it changed. And the second ingredient is some kind of utility measure for a group of agents, but that could be as simple as the joint reward. And with that, the sort of very obvious definition of resilience is that we require simply that if the change in the environment is bounded by some constant, let's say K, then the performance should be at least some other constant depending on K, CK times the original performance. So if you got 100 rewards in the original MDP, you want at least 95 reward in the new MDP for any MDP that's just a little bit changed from the original. If you think about there being an entire space of MDPs, what we're saying is that if you have a source MDP that you trained in, then within some K distance, all or region around that source MDP, you want the guaranteed minimum performance. And we're proposing that as sort of a metric to think about, to optimize for. We don't have a specific solution in mind. This is a problem definition. And that's sort of the starting point for our work. In practice, that might not be the most workable because it's a worst case guarantee. So if you want to verify this experimentally, you're almost never going to be able to check all of the possible MDPs within a certain distance. So we have a second in expectation definition that works exactly the way you would expect it to. Given a distribution over MDPs, within still k distance, can you guarantee that in expectation your performance is going to be at least a fraction of the original? There's many more variations possible. For instance, you can notice that the way we define the way we use the utility here, it looks like we're just looking at absolute performance. That might not always be the fairest thing to look at. For instance, if you're in an MDP or in a world where you have to go around different places and unexpected changes or roads being closed, if a road is closed, that just makes all the travel times tenfold, and you only get 10% of the original performance anymore. That's maybe not because you're not resilient, it's because the environment changed. So if you know the optimum in a given MDP, you could also look at relative performance, for instance. But in most cases in practice, you don't know the optimum. So there's different trade-offs depending on whether you're looking at theory or practical work. In practice, in our own work, for distance measure, we've used a very simple approach. We've just taken whatever source MDP we're in, and we apply iteratively very small perturbations to it. For instance, in a geometric world where you move around, we can place obstacles and then just count how many obstacles we placed or changed. Formally, we defined it as the number of state transitions we changed or the number of actions we changed. That works very easily in practice if you have a nice environment where you can do these kinds of modifications. In the literature, there's also more abstract measures that sort of count also state transitions, and they work out to something very similar in practice. And for utility measure, we have been using the group reward after some amount of adjustment time. So we're not looking for a 0 shot necessarily here, we're looking for relatively few shot. We have some, so as I said, this is, at this point, we just want to discuss sort of the problem setting, and we're interested in what people think about it. We have some initial results together with one of Sarah's students, Ophir, and with Jeffrey Rosenshine, also in Israel, about communication helping resilience. So here the idea is that if an agent encounters something in the environment they weren't expecting, they communicate that to other agents, either using a hard-coded protocol where we literally send out this transition we just observed and give it to the other agent's replay buffer, or an emergent communications protocol. And either way, this in experiments does help resilience. We're looking at a number of further extensions, different types of collaboration. Sarah also wants to put this onto real-world robots, which would be fun. We're also thinking about whether we can use this as a theoretical tool. If you have a nice succinct description of the MDP, can you maybe reason about how agents should behave if the MDP is changed? And it's also related to a number of different areas. For instance, there's a lot of literature on unsupervised environment design and automated curriculum design that sort of sample from a distribution of MDPs as well. But conceptually, it's a little bit different because we're just defining the problem, not the solution. So all of those are curriculum learning approaches that are a methodology rather than the problem. And the other thing is that that body of literature is more about already knowing the kinds of changes you're going to encounter and the kinds of MDPs you want to train in. Whereas we are really thinking, can you train in one MDP and through leveraging each other, still adapt quickly to something completely unseen? That's sort of where we want to go. Yeah, and we think it's sort of an interesting connection to ad hoc teamwork, and we're curious what everybody thinks. That's it. I think we're not going to do Q&A, you said, because we're behind time. But come talk to us offline.
Yeah, I do have a question though.
Okay, yes, maybe one. I'm at 9 minutes, so maybe we can do one.
Perfect. So no, it's the connection to real world robots. I've seen that this resilient, well, basically it kind of relates to the fault tolerance control, and some real world robots, what they basically do is have like a worm model, and then they basically analyze. It's more empirical.
Yeah.
But they analyze when the transitions are different. is basically meaning that there's been an error, some kind of different.
Is it more about errors as in like machines failing or the world changing?
Machines failing.
Ah, okay, yeah.
So it's like a different kind of view of the problem, right? But still kind of relates. But I guess yours is super like theoretical. It's more like more of analyzing the problem conceptually.
In this talk, yes. So we have this initial work as well, where we do experiments, and we can show experimentally in some standard multi-agent RL domains, if we sort of introduce some unexpected change, our agents recover faster.
Okay.
And as I said, Sarah does want to put this on actual hardware robots.
Yeah.
But we also think it's an interesting theoretical concept to think about.
Have you tried it on GridWorld so far, or have you tried?
GridWorld-like things. So we've built this domain that's sort of a multi-agent taxi environment where multiple agents move around, ferrying passengers from different points.
Then you definitely collaborate with Guy. Yeah, I've seen that environment.
Yeah. So this kind of thing where you can then that makes it easy to introduce perturbations because you can just block rows. Yeah.
Okay, great.
Cool.
Okay,
thank you so much.
Here's an extra kit on your list.
Definitely. Talk later.
I think it's Yair next. Sorry if I mispronounced the name.
Yair? Yeah, no.
Yeah, Yair is here.
Okay, hey. Yes, are you ready to present?
I did not understand what you said.
Oh, sorry. Are you ready to present your presentation?
Yes.
Okay. You can go ahead and share your slides. And yeah, we're trying to keep it a little bit shorter, but so if you're okay with that, then we try to be fast so we can get through this session. But yeah, please go ahead and.
Okay. I did not understand most of it what you said, but I understood basically.
Okay, perfect. Yeah, sorry about that. And go ahead, present, please.
Okay, so my name is Yair, and I will be talking about our recent work quantifying human rationality in ad hoc TeamWorld. So let's go over the motivation. So as we come to realize, humans sometimes do not act optimally or legibly. So if
sorry,
we have,
Yair. Sorry, but we don't see the presentation. We see the PowerPoint.
Oh, good to know. Thank you.
Perfect. Thank you.
Okay. So I'll start over. So as we come to realize, humans sometimes do not act optimally or legibly. So if we have a human agent and an artificial agent that are trying to work together in order to complete a task, when the human agent will not act optimally or legibly, the artificial agent will not understand what is the aim of the human agent. So as a result, the time to complete the task will be delayed. However, if the artificial agent will have a human behavior-based policy, it will understand to some extent that the human's actions were at least rational and will be able to predict the human's goal and cooperate in order to complete the task. So our aim is to create that human behavior-based policy. So after we will add that policy, the artificial agent might say something like, all my life I've relied on logic, but I've got human nature too. So how do we model human rationality? There are many approaches to represent human rationality and predict human behavior under specific interaction protocols. In the domain of psychology, there are two papers here, but we will focus on an approach called bounded rationality. And specifically, we use the model of quantum response. Now, bounded rationality means that humans have a limit to their capability to predict what is the outcome of their own actions. So when it comes to a challenge, it depends on their prediction depends on their capability, their cognitive capability, the time that they were given in order to complete that task, and the complexity of the task itself. So we will look over the logit-Quantal response equation. So UP is the expected utility of policy P. Lambda is the rationality parameter, which is in range between 0 and infinity. And P of Pi is the probability to follow a specific policy Pi. Now, as we can see, lambda, that is the rationality parameter, has a range between 0 and infinity. So if we choose, if the lambda is equal to 0, we will check the edges. We will get that every policy has the same probability. I will take the laser. Yeah, every policy has the same probability, and it does not depend on the expected utility of that policy. And when lambda approaches infinity, we will most likely choose the policy with the highest expected utility. By that, the lambda, which is quite high, multiplied by the highest expected utility, will give us the highest probability for that specific policy to be chosen. So most recent work on ad hoc teamwork relies on MDPs, and so we did the same because it's the amount of policies is too big to enumerate. So instead of a policy, we will use MDP and state and action dependent utility function instead. So PAIS is the probability, which is the probability to take action AI in state S, and is also an estimation of the human's transition function. So instead of the policy I that we might take, we might take AI in state S. And instead of all policies, we will have all the possible actions. So instead of logit-Quantal response, we will have state-dependent Quantal response. So how do we feed the state-dependent rationality parameter? So by using the new equation with the state and action dependent, we can predict the probability of a person taking an action A, and in order to estimate the rationality parameter of the person in that state, we use RS that is between 0 and 1, such that lambda S is estimated by 1 over the absolute value of log RS plus epsilon minus 1 over absolute value of log epsilon. Now, epsilon is an arbitrarily small number that we used while we were experimenting. It doesn't change much the result. So now RS is the ratio of optimality. It means that it is the number of optimal actions taken from state S over all the visits to state S. So let's go over the quantifying results. Let's go over the tool fetching domain. Now, as we can see, it's a grid world with states and actions. So the human agent here can take an action up, down, right, and left. When it goes to one of the patients, it can use walk. When the human does not know what to do, it does noop, which is do nothing practically. There is the artificial agent that needs to take the medicine from the toolbox and get to the human's destination. Now the human's destination is, in this case, is this particular patient with the star. And we should know that the human cannot take any of the medicine from the toolbox, but only to get to the patient, and the artificial agent can take the medicine from the toolbox. So now the data itself that we created, that we used here, is from collected human data using mTurk. It's the same data as the paper reasoning about human behavior in ad hoc teamwork, which has 45 participants and 16 board setups. So now let's go over the values. As we can see here, there is a gray states, which means that the humans never visited those states when they faced the challenge. And there is black state, which means that the rationality value is 0. Why is that? Because only one participant moved there and moved to the wrong, moved not optimally to the right. And why this state is high, which is the value of 1, is because that particular participant moved correctly this time and moved down. So it's 1 optimal over 1 visit. So let's look over the rectangle between the patient and its goal. We can see that the color is quite bright orange, which means that most of the participants moved in this particular space. And as we can see, it's not always 100%. And that's because sometimes the participants moved incorrectly.
Sorry, just a minute left. If you can wrap up soon, please.
Okay.
Thank you.
Okay, I understand. So they move when the participants did not act optimally, it didn't affect much the results, because we can see that the color didn't change much as they moved not optimally. Now, in conclusion and future plans, we presented here a bounded rationality model for state-dependent policies of human agents. This model can predict how optimal participants are in any state on the board. We can see the colors. We will incorporate the quantum response model into the design of ad hoc teamwork agents that need to collaborate with people. And we will compare between the results of the ad hoc teamwork agent with assumed optimal policy and with human behavioral-based policy. So, thank you.
Thanks. Okay, I think we probably have to skip the Q&A, but if anybody wants to, has any questions or comments for Yaya, then I think it would be good to someone. So I think the next speaker is Kyle. So is your
I can send. Yeah.
Yeah, please.
My email? Sure. Yeah, just send it from the email.
Okay. Do you want to send?
Oh, yeah, he's not in and out.
Yeah. Actually, then, so while we're waiting for this to be set up, I also I think this quantum response idea is quite interesting. I don't know if you saw. Actually, I think I sent before some paper which does something similar. I thought it's something similar anyway, so maybe it's good to take a look at this. But also, I saw one of the other workshops here at IJCAI. There's somebody who I think disagrees with you on the quantum response model. So maybe it's also good to look at their paper and have an argument with them about how good this is. I think this is at the communicating with humans AI or something like this workshop. So if you're interested in that, then maybe take a look also at that.
If you can find the name of the person or the title of the paper, we'll appreciate it.
Yeah, I will send it over. Okay, and it looks like we
Yeah.
have the slide for the other for Kyle's presentation now. So we will share this and okay, and is the camera's on, right?
Yeah, it was on.
Okay, then over to Kyle.
How do I like change slides?
Just use arrow key.
Doesn't do anything.
Oh,
Oh, okay, yeah.
Okay, now it works. I'm just gonna take my mask off. All right, hello, I'm Kyle Tilbury. This talk is going to be pretty high level. This is very kind of preliminary work, but hopefully it's motivating and highlights some interesting problems in the area. So I guess we're interested in eventual human agent teams. So, you know, humans are inherently complex. In order to, you know, deal with that, agents are going to need a very diverse, you know, set of skills, especially when it comes to like human social phenomenon. Specifically, this we're looking at identity and sort of dynamic groups / teams in this case. So what do we mean by identity? Identity is a pretty nebulous term. So when we say identity, we're referring to this, I guess, work by Akerlof from economics in terms of economic identity. So this is a model that encapsulates sort of the standard components of economic utility. So that's things like someone's preference for like goods or services, like if you prefer apples over bananas, something like that. So those are things that are sort of characteristic to an individual. It also includes this identity element, though, which is comprised of these three sort of, I guess, like things that make it up. So those are social categories, norms and ideals, and any utility. So this identity element is a thing that is derived from the social setting and varies with social context. So we're going to go into an example just to kind of explain what we mean here. So consider a bunch of children on a merry-go-round. Children are very aware of their age and sort of understand the norms associated with their age. So like, you know, they understand, you know, big kids are supposed to act differently than little kids. So in this case, the social categories here are the age groups of the children. So say we have like toddlers and then 4 or 5-year-olds and older kids. And then we have the norms and ideals associated with this. So that's how someone should act according to like their category, like, or how they should not act. So maybe on this merry-go-round, toddlers will ride with their parents, 4 or 5-year-olds being more like independent and like bigger. They'll, you know, ride by themselves. They'll be proud of that. They'll be like waving and be like, look at me. But then something like an older kid would, like, let's say a 13-year-old, they would probably have to act like, you know, I'm too old for this. I'm too cool to enjoy merry-go-rounds now because, you know, I'm 13. I got to be edgy. And so they have to act like maybe they're not enjoying it. And then this identity utility is sort of how the norms actually shape the behavior. So this is sort of how like the loss or gain in utility for conforming to the norms or behavior of your category. So in this case, like that 13-year-old can't enjoy it due to it not conforming to their norms for their like social category, and so like they get off the merry-go-round. And then sort of this kind of leads into this dynamic teams. So human teams are not static. That's like, so within an organization, individuals might come or go, or sort of move between groups within that organization. So within that system. And so like the workplace is one place where this is very evident. So just in terms of identity in the workplace, workers tend to identify with their close work group and not sort of the organization as a whole. So maybe more their team rather than everyone else at work. And then the like identity, economic identity for that is like, yeah, the social categories are they're either an outsider or a member of the work group. Norms are like work group members think they should put in medium effort. They think outsiders low. And then yeah, identity utility is if they sort of conform in that. So if you were like a member and you're putting in low effort, you would be deviating from the norm and having like reduced identity utility. So yeah, if agents, I guess, are coming into a work group with humans, this is probably going to be at play because, you know, the humans are acting in ways that sort of align with this model. So I guess we want agents to be able to understand and sort of interface with that. So how are we actually going to be experimenting with identity and sort of these dynamic ad hoc teams and multi-agent systems? Well, we're going to start very simply. So just this environment. So this is the cleanup social dilemma. This is from like Hughes et al. So this is like a little social dilemma environment. Agents can essentially clean a river, clean waste from a river, or harvest apples. And waste accumulates in that river at a steady rate. And the more waste there is, the less apples grow. And there's multiple agents. And this is a social dilemma in the sense that agents are incentivized to just go eat all the apples and not contribute to cleaning the river. So this is typically not done with teams. All the agents are independent and then sort of have to learn to collaborate in order to, like, I guess, solve the social dilemma. So yeah, we basically want to, I guess, imbue agents in the cleanup setting with this identity element. So yeah, we have to, I guess, characterize these different, I guess, aspects of economic identity in the agents. So like from a nice simple perspective, we just want to add like social categories. So that's apple pickers and river cleaners, since those are like the two things that can be done in the environment. And norms and ideals we'll kind of go into when we talk about the teams next. And I guess identity utility, we want to, so not necessarily just like, okay, the apple picker is picking apples, so he gets +1 reward. We want to look at more like specializations and not just like tailoring reward functions. So maybe like if you're an apple picker, you're better at picking apples. So maybe you can like pick more at once, or if you're a river cleaner, you can clean more of the river at once. So just sort of, yeah, just have it be more specialization based than, yeah, just adding additional utility. So yeah, like next we're going to talk about sort of how this might go in conjunction with teams. So that's sort of how we want to get at this other social context in the same environment. So identity again depends on the social context. So yeah, we're imagining sort of, I guess this is sort of the ad hoc team part, but not conventionally. So more like a fluid ad hoc thing where agents can join or leave teams within a system, but not leave the system. So there's like open ad hoc teamwork, which is agents may come and go from a system. This is they're staying in the system and they can join or leave teams within that system, and they have to learn how to, I guess, work with others within those varying teams in the system. Again, this is sort of like, you can think of like earlier in like an organization where you might have like different teams performing different tasks within the organization, and yeah, members may move throughout those. then yeah, this idea of norms within the teams. So norms are, I guess, powerful shapers of behavior. So like our norms are like, you know, manipulated constantly on a daily basis. Even like ads are trying to like sell you on like an identity, you know, it's like smoke and you'll be cool. You want to be part of that cool smokers group. So I guess we're interested in sort of how we could define different teams with predefined norms, and then these agents have to join these teams and I guess infer the norms and infer the other members' identities. And we want to understand, I guess, if that's like even possible, if they can still like come to you know, like solve the social dilemma despite these identity pressures, and how that sort of all is intertwined. And yeah, so that's it. Pretty high level, pretty speculative maybe. But yeah, so I guess the long-term goal is effective human agent teams. So we need agents that can deal with social, psychological, human phenomena. And yeah, we think identity is important, and essentially also like how identity interplays with team dynamics. Yeah.
Yes, we've got to move on to.
Yeah.
Thanks for the.
Really interesting.
Yeah.
So while we can ask questions, but we'll have a long break afterward, and
I think we should definitely. Yeah. I think
yeah, we'll have like half an hour afterwards. But we have people joining in after this, so
Yeah.
The
next thing is the poster.
poster and highlight, right?
The poster, I guess. I didn't know whether that's going to work.
Yeah, I don't know.
Maybe we just.
We'll see.
Maybe we'll have a chance to ask some questions. Just maybe a Russia question. I remember.
Can everyone see this?
Yes.
Okay, cool. I don't know if you can see me. I'm gonna sit down because I don't know what you're looking at. So I'm gonna be really fast. We don't have much time, but basically I'm gonna switch gears a little bit, and I'm gonna start talking about the oceans. Well, as you know, the oceans are really important. They cover, I think, 71% of the surface of the Earth, which is a massive amount, and they're home for many natural resources that we're trying to exploit. There's a lot of money involved, but there's also fantastic creatures and environments like the one in the picture that we really want to monitor, survey. We want to make sure that with all these issues with climate change, these environments are still maintained. So there's a lot of interest in industry and also from the research community to monitor the oceans and exploit those resources, right? Now, but this is really, really expensive. So usually one way that researchers are trying to do to make this cost of exploring and monitoring more low cost is to use autonomous solutions, right? So something like this, which is an autonomous underwater vehicles, an AOV, is a low form robot that you can just deploy in the ocean and just tell them to go and do whatever it is that you want to do. Of course, this is not as easy as it might sound, as you can imagine. You have a lot of issues like limited capacity battery. You cannot put anything you want in there. There's small sections of sensors that you can put in it. And the most difficult one is that you don't have GPS on the water. So it's really hard to localize yourself in it. So one thing that we're working on, or we were working on, or researchers in the underwater community are working on, is basically to use a team of robots to do this. You can have like communication effectively done on the water by having like a surface vessel or transponders like this one, and then have these robots communicate with each other to help localize itself. Now, most of the work done in this type of scenarios are assuming that you know which robot you're collaborating with, so you have a lot of this information. But I have an example, a motivating example, which is interesting to discuss, which is the disappearance of the Ara San Juan. I'm from Argentina. This is a submarine that disappeared from the Argentine Navy a couple of years back. Basically, it was supposed to come out for air to communicate with land. It never did. So it went missing completely. So a chaotic search started to try to find it, because they knew how much air they have left where you can, the crew can stay alive. So the whole world came to Argentina with many robots, boats, ships, and try to search together for this lost submarine. It was unsuccessful, unfortunately. They did not find the submarine. They found it years later by using also this type of coordinated robot technique. I'm going really fast, sorry, but that's the whole the time that I have. But this unfortunate incident brings this question, right? So how can we have robots that can actually coordinate and cooperate on the fly for this type of scenarios? When you have a search and rescue mission, for instance, and you have different robots from that have different sensors and capacities, how can we develop this type of agents that can actually cooperate on the fly and try to find, for instance, one of these missing vessels? Now, of course, in this paper, I do not solve this problem. This is just an enumeration of challenges that will have to be solved in order to effectively develop these type of agents. And one of the first things right off the bat that we can counter is noisy environments and partial observability, of course. That is one of the first things. But the second one is that perception capabilities are limited. And I don't mean that in the sense that it's partial observability. I mean that there's a limited set of sensors that you can put in there. And these sensors may vary between vehicles. So like I said, in the surface, you may have an ASB that has GPS, but under the water, you don't have that. So these two robots with different sensing capabilities will have to collaborate. And one way of doing it, of course, like we said before, is communication. Then this brings another issue, because in underwater, you have a lot of delays in the communications and you have low bandwidth. So that creates a lot of issues in which communications are really unreliable. So you need agents that can actually make decisions when they're uncertain still about what other about actions from other agents, right? And this is another issue that appears, is that not all agents can move the same way. Same example, AUV on the water, and then you have a boat on the top. The boat can only move on the surface, but the AUV can move around. Or you have some AUVs that have arms and then can collect things. So how are this different way of moving around and intervening can be taken into account? Well, this is another challenge too. There's a few papers working on this, but it is that the fact that in this type of search and rescue operations, you do not know in advance how many teammates you're going to have in your team. So this is completely unknown. And the last part, and this is a really difficult one, is that we kind of need simulators that allow us to emulate the different parts of the problem, right? Because we have really complex dynamics in the underwater environments. So you need to be able to simulate that, but you also need to be able to simulate the other parts of the problem, like the communication or the type of issues that you have on the sensors, like noise, latency, and all that kind of stuff. So basically, in conclusion, we can say that marine operations are moving towards this team of robots, of network of robots kind of scenarios. But for some specific situations, it seems like adult teamwork is a good thing to have in these teams. But well, there's many challenges that need to be solved. Hopefully, we'll try to tackle some of those in the future, but we will see how well we do with that. And I think we're right on schedule.